So, where do numbers come from? When and how were they invented or perhaps discovered? What does it mean to be a number? The numbers that are required to describe the solutions to these equations were numbers that not only people in general, but mathematicians themselves objected to strongly when they were first created or invented. Each of these is a quote from a mathematician of the era describing their reaction to the new number systems being suggested. How can nothing be something? We didn't believe zero was a number for the longest time. Fractions, they didn't make the cut for a while. It's interesting to see how many different cultures have had some form of fraction and yet not what we would consider fractions for many, many hundreds of years. You can do a lot of sophisticated maths without thinking of fractions as numbers. There'll be a lot of work with ratios in terms of 3 to 5 rather than thinking in terms of a fraction like 3/5. False, absurd, and meaningless. You may have used these phrases yourselves when you first learned about directed numbers or negatives, because you can't have a negative number of sheep, for instance. It doesn't make a lot of sense when you're trying to count objects to have a negative number. If 3 people walk into a house and 4 people walk out of the house, does it mean there's -1 person in the house? Well, probably not. And yet it turns out, as we're going to discover for all the other number systems, they're really, really useful for certain types of problem that you might want to solve. We find them helpful for money, for instance, negatives, and they can be really useful whenever you have a direction problem. They're called directed numbers because they somehow give you an indication of which way things are moving. If you have gravity pulling you down and yet the thrust of the rocket pushing up, you can combine those things and interpret the result. Negatives are how we deal with numbers that are pointing in different directions. Inexpressible. This is a lovely one. They darken the very whole doctrines of the equations. You should look at that quote. There's more to it. He rants on a while about this. Irrational numbers were called irrational because they cannot be written as the ratio of whole numbers. But we've now taken the word irrational to mean nonsensical, absurd. In fact, the word "surd" comes from the same root as absurd. We're talking about numbers that don't make any sense. And that was synonymous with numbers that cannot be written as the ratio of whole numbers. There are some numbers that can't. √2, pi, things like that. People did not like those. Pythagoras had some real issues with that. And the final one, this is the one that you might have seen coming. Imaginary numbers. These quotes are mostly taken from Cardano, who, strangely enough, was the person who first started using them. And even he didn't like them, claiming they were useless while at the same time using them to win competitions. Very strange. The numbers that we know and love usually fall into one of these categories. If you look carefully at the top of the screen, we've got a funny looking n. That represents the natural numbers. Another word for those is the counting numbers. They are the numbers we first learn when we begin counting: 1, 2, 3, 4, 5, etc. Z, from the German Zahlen for numbers, this is the integers. So they now include the negative numbers like -3 and also 0 in between. So now we can count not only forwards but also backwards. Q stands for quotient. These are the numbers that can be thought of as a quotient of two numbers. In other words, one number divided by another. So if you get an integer and divide it by another integer, then what you end up with is a quotient of two integers. A rational number is how we normally describe those. The R stands for real numbers, an unfortunate terminology because in some sense all numbers are real, in another sense no numbers are real. But the real numbers now incorporate not just every single rational number, but also all the irrational numbers. The one we're going to start looking into next is the complex numbers that somehow contain all of the numbers you already know and some more. So let's see how we go about inventing a new number system. We start by imagining a number that multiplies by itself to give a negative answer. That's what we would have needed to solve that final equation. So let's see if we can imagine that one exists and see what it looks like. Well, to start with, we know we have a few issues. It's not going to be the sort of number that we've seen previously. We can fairly quickly prove this. If you square a positive number, you get a positive answer. If you square a negative number, you also get a positive answer. And the only other alternative is 0, and if you square 0, you get 0. So what on earth could we start with that when you square it gives you a negative answer? You can even draw a graph to make sure you've convinced yourself you've covered all the options. it is very clear that the graph y equals x squared does not dip below the x-axis. So no matter what number you put in from anywhere on that number line, what we might call the real number line, none of those input values give a result which is a negative result. You can't get a negative by squaring something. At least you can't get a negative by squaring the kind of numbers we're used to. We're going to need to create an entirely new number that does that. It's worth remembering at this point, if you think it's a bit strange to invent numbers, that's what all numbers already are. The number 7 is not something that somehow is any more than the number -7 or minus pi over 3 is. They are figments of our collective imagination. In fact, if you think, there are lots of things that are the same that we don't really question or worry ourselves with. Money is a collective delusion in some sense. It's real because we believe it's real. The only reason I value a £10 note is because I know that you value a £10 note and that I could exchange it for goods and services. But the only reason you value it is because you know that I value it and that everyone else values it. And all it takes is for somebody like the Chancellor of the Exchequer to say, you can't use that old £5 note anymore because it's gone out of circulation, and suddenly the thing that used to have value doesn't have value. Words are another good example. Are words real? In some sense, a word is more real than any representation of the word. Writing it down is not what makes it real. The marks on the page are not the word. They are a representation of an abstract concept. So either words and ideas and money and numbers are all real, and in some sense more real than tangible objects, because they don't fade or disappear or get burned up in a house fire. Either they're more real or they're all just as imaginary as each other. So let's begin the creation process. Let's construct an imaginary number. First thing we need to do is give it a name. Just like in algebra, we don't know what something is, we label it, and then we can start talking about it. We're going to give it the same name that Descartes gave the imaginary numbers, I as the imaginary unit. In other words, it has size 1, but it's imaginary. He was also the one who gave the imaginary numbers their name, imaginary, mostly as an insult so that people wouldn't take them as seriously as the so-called real numbers. But the name imaginary numbers has stuck, and the letter I tends to be used to represent the imaginary unit. And the defining feature. Now in maths, when you ask somebody what something is, they usually respond by telling you what it does, how it behaves. See if you can describe multiplication without just giving examples of what multiplication does. What a thing is what it does. And I is the thing which, when you square it, you get -1. That's what it is. But what else? We could do with a bit more. Ideally, it would be nice if this number fit all the rules of the previous number systems that we've worked with. When you start dealing with fractions, you don't have to throw out all the rules that you learned for whole numbers. You just have to add to them. You have to take on board everything that works for whole numbers and augment it by producing some new rules for what happens when you've got non-whole numbers. We do a similar thing here. We'd like this number to have all the same properties that we already know and love. So here's a few expressions. I'd like you to have a think about how they should simplify if this number behaves in all ways like ordinary numbers. The only difference being, if you ever see I squared appear anywhere, you can replace it with -1. So we can scale things, multiply it by things, and we can add. You can have 3i, add it to 2i. Think of what you'd do if this was 3 root 5 plus 2 root 5, or 3x plus 2x, because they're numbers that you already know how to deal with. What about powers? 4i in a bracket squared. What about I cubed? If I squared is -1, can we write I cubed in a simpler way? And then complex combinations. We already know how to expand brackets. What happens if we expand these brackets? Does anything interesting happen? And if you really want to stretch yourself a bit, jot this one down and give it a go when you have a minute. Squaring 1 over root 2 plus 1 over root 2i. If we add two imaginary numbers, 3i and 7i, then we'll get another imaginary number, like 10i. But if we add a real number to an imaginary number, they don't cancel out or disappear. It's like adding pounds and dollars. Unless you've got a way of converting between them, then $3 plus £7 is $3 plus £7. But what we can do is write those numbers as a real component and an imaginary component added together. If you have 3 1s and 2 i's, you can write 3 plus 2i. And now all of the numbers that you know, the real numbers that you're already familiar with, can be combined with all of the new numbers you can create by multiplying a real number by I, the imaginary unit, and that gives you a set of numbers called the complex numbers. Now, the great thing about the complex numbers is they are a closed system. What this means is if you add two of them, then you just get another one. You can add the real parts together, you can add the imaginary parts together, and what you get is a new complex number with a real part and an imaginary part. Not only that, but you can even multiply them. Pick a couple, try multiplying them together. You'll find it feels a lot like quadratics. You can expand two brackets, then you can multiply two complex numbers together. You might think I've made a mistake with my color coding here, because surely 2i squared is imaginary, not real. And yet, if you remember, even though I is imaginary, I squared is -1. So I squared is a real number. And that allows us to simplify these things. Even when you multiply two complex numbers together, what you end up with at the end is just another complex number, in this case 1 plus 5i. So we never go beyond real part plus imaginary part. You can even divide them. It's a bit of a mess, so don't panic if this looks confusing, but the trick here is to use exactly the same method you use when you are rationalizing a denominator. If you had 1 over 1 plus 2 root 7, you would multiply the top and the bottom of the fraction by 1 minus 2 root 7, and then the difference of two squares magic happens on the bottom of the fraction. You end up with something which no longer has root 7, because anywhere root 7 appeared, it either disappeared or got multiplied by another root 7. The same thing happens with i's. They either disappear or they get multiplied by another I, becoming real. Even though Descartes gave us the Cartesian coordinate system, x's and y coordinates, to be able to plot graphs, and he was aware of imaginary numbers, gave them their name, he didn't recognize the single most important thing about complex numbers that people later on managed to use to popularize them. Mathematicians didn't really get to grips with complex numbers until we started thinking of them as being points lying on a complex plane. Cardano came up with the idea in 1545 to have imaginary numbers, to use complex numbers in equations, but he had no way of visualizing them, no way of thinking of them as real objects in any way. He was dealing with the square root of -15 inside equations, and he was able to use it and take advantage of the fact that that thing seemed to behave like other numbers, and then get rid of it towards the end and find the solutions he was trying to get to. But he didn't like them, and he only used them when he had to. It wasn't until mathematicians recognized they could draw them in a particular way, and as a result they start to see the structure behind them, that they really started to catch on and become a big deal. The first thing you got to think about is, well, where does I sit on our number line? It's not positive or negative, because if it was positive it would square to give a positive, and if it was negative likewise. And it's not 0, because then it would square to give 0. It's somehow halfway to -1. Halfway to -1 from where, though? That's the question. Well, if you were to square root the number 4, you get 2. Well, that's halfway from 1 to 4 if you go up in multiplying by 2 steps. Well, what kind of steps do you need to go up in to get to -1 from 1? You don't go via 0, so you must go via somewhere else. If you can think of how you would turn the blue arrow into the red arrow, well, you might think of it as a reflection. You'll find it more helpful in this case to think of it as a rotation. When you multiply by -1, you rotate the number around the origin, the 0 in the middle. This is the halfway point. If you go halfway from 1 to -1, you're only rotating 90 degrees anti-clockwise. And you get to a point which is equivalent to the point 0, 1 on an ordinary XY graph. And down here, if you continue, if you multiply -1 by something twice, you get back to 1. Well, the thing you multiply -1 by to get 1 is -1. So you can think of it as a 180-degree rotation again. That's why when you multiply a negative by a negative, you get a positive answer. But what if you only go halfway? You end up pointing down. This idea of having a two-dimensional description for complex numbers is the key that breaks it all. This is the number 1. We call this the real line, and we think of it as the real axis when we're dealing with complex numbers on a complex plane like this. If you multiply by I twice, then you get -1. So if you multiply by I once, then you must be halfway between 1 and -1. The only way to be halfway between 1 and -1, and yet not at 0, and yet still the same distance from 0 as 1 is, and as -1 is, because I is the same size as 1 and -1, the only way you can do that is by sitting on a circle of radius 1 about that origin point. And if you multiply by I once more, you get -I. And if you do it again, you get -I times I, or -I squared. But I squared is -1, so you get -1. You just get 1. You get right back where you started, and you can multiply I by itself as many times as you like, and all you will do is go round from one of these places to another. The beauty of this is that you can visualize any and every complex number as a point on a two-dimensional surface. Just like all the real numbers lie along that line that we call the real line, all the imaginary numbers lie on what looks like a y-axis, a line perpendicular to the real line. And every other number is composed of a real part and an imaginary part, and it will lie somewhere on the two-dimensional plane. Every time you multiply by I, you rotate by 90 degrees anti-clockwise. Now, there's all sorts you can do once you've got that key insight, and we definitely don't have the time to get into it today. But there are a few useful things we can see. One of the valuable things about having a change in perspective is that you can start to recognize patterns that you couldn't see easily before. Now, addition we can think of as translation. When you add the number 2 plus 3i to the number 1 plus I, you get 3 plus 4i. You are moving in the Cartesian plane, if you like, following the instructions that the 1 plus I gave you. But multiplication is even cleverer, and this is where complex numbers really get their power from. If you multiply by I, you get an anti-clockwise 90-degree rotation, like we saw. What do you think would happen if you multiply by 1 plus I? I'd encourage you to pause at this point and try it out for yourself if you've got the time. Have a go at multiplying 1 plus I by 1 plus I, and then get your answer and multiply it by 1 plus I again, and see if you can plot the results on a little graph. What you should end up with is something that looks like this. So you can see the original point 1 plus I is there, moving along 1 to the right in the real direction, if you like, and 1 up in the imaginary direction. When you do 1 plus I squared, you actually get a purely imaginary number. 1 plus I squared comes out as 2i when you sort it all out. When you multiply by 1 plus I one more time, you get -2 plus 2i. You do it again, you get -4, so it's a purely real number now. Much like when you do I to the power of 4, you get the number 1. If you do 1 plus I to the power of 4, you end up with the number -4. It has no imaginary component whatsoever. If you keep going, you find that we're following some kind of pattern. Not only is the size of this arrow increasing as we go along, but the direction of the arrow is following a pattern as well. In fact, the next level on from this idea is to start thinking about those points in the complex plane, not in terms of how far along and how far up, but in terms of how far away and at what angle. A little bit like with a distance and a bearing, but in this case we usually measure the angle as the anti-clockwise angle you turn from the positive x-axis or the positive real line. And we think about the distance from the origin as being the size of the complex number. So 1 plus I has a particular size. In fact, a bit of Pythagoras will show you the size is about 1.4. It's √2 to be precise. And if you multiply two complex numbers together, the sizes multiply. That's why when we squared a number that had size √2, we ended up with a number that had size 2. 2i has length 2. And if you keep going, you'll be multiplying the length by √2 every time, even while you're adding 45 degrees to the angle. If you want to look into this a little further, complex numbers are the thing behind this beautiful fractal. You've almost certainly seen it kicking around. It's the kind of thing people put on PowerPoints for no particularly good reason. But I've got a reasonably good reason for this one, because it's based on complex numbers. It's not a particularly complicated formula either. What you're doing is something like squaring a complex number and adding it to another complex number. And if you do it over and over again, sometimes what happens is you end up ballooning off to infinity. So the numbers get bigger and bigger and bigger, and it just disappears. But other times you end up sort of staying put. If you were stuck on just real numbers, that's not a very interesting process, because you find that if you repeatedly square a number between 1 and -1, then it might stay put. But if you repeatedly square a number that's beyond the 1 to -1 range, then it's just going to balloon off to infinity. With complex numbers, it's a little more complex. And the black on the screen shows you the points that converge, that don't balloon off to infinity, and the white on the screen shows you the points that diverge, the ones that are going to disappear off and never converge to a fixed point. If you have the time, I highly recommend you look up the Mandelbrot set and you see if you can find a visualization of it on YouTube. It's very interesting and somewhat mysterious, and definitely going to look into it a bit more when you get to the further maths part in the second year. There should be a Microsoft Forms quiz available. The link should be just below this video if we've done this properly. And if you've enjoyed this process and you've found this fascinating and you have lots of why questions bubbling up in your head, then you might just be the kind of person who would enjoy the Fast Track Maths and Further Maths course. Thank you. I've been Anthony Closey, and I will possibly be teaching you in future years.